So, for those who don't know this exact lecture series, my name's Palladium, and this is going to be chapter 15 of a British textbook known as Chemical Structure and Reactivity, and this is for general chemistry. And overall, I did start the series about a year ago. It was on hiatus, but now it's back, and the next lecture is going to be actually in 2 or so days, so do expect something at that time. In addition, here's the shout-out list. Just DM me if you want to be on the list. I'd be happy to put you on there. Alright, so let's get into it. So, this chapter is going to be the last that's going to cover organic chemistry. Chapters 11 and 14, those covered the basics of organic chemistry and stereochemistry, respectively. However, if you thought that we would end with that, you'd be wrong. And that's because this chapter will cover a lot more when it comes to alkenes and aromatic molecules. And in addition, we will briefly go over some more molecular orbital theory and also sigma conjugation, which dictates how alkenes behave in reactions. And also, we'll be discussing about enols and enolates. And finally, we'll be talking about electrophilic addition for aromatic molecules. So let's get it straight into it. So if you've already checked out chapter 11, you should know what SN1 and SN2 are. Just for a quick recap, imagine that we have some sort of tetrahedral carbon compound, right? Essentially, we can substitute for a particular leaving group for some other type of substituent. And SN1 and SN2 both do it, just in different ways. SN1 first forms a carbocation, while SN2 does it all in one go, ejects the leaving group and substitutes in the new group. However, when I first looked at this reaction diagram for the chapter, I saw that we are getting substitution products. We can see that there's no longer going to be a bromine here. There's going to be ethoxide. But in addition to that, we also do get substitution for other reactions. But somehow we also get alkenes. How does that work? And so, the exact mechanism that creates these alkenes are known as elimination reactions. And in this case, HBr is eliminated. So, because we're on the topic of alkenes, I also wanted to talk about sigma conjugation. So, sigma conjugation is a phenomenon that occurs when, say for example, you have a very long alkene and you have the double bond in the middle. So, a double bond consists of a sigma bond and a pi bond, according to valence bond theory. Also has pi orbitals and sigma orbitals, according to molecular orbital theory. So, if you have a very long alkene, what can happen is, if you have the carbons next to the alkene carbons, those are bonded to hydrogen, for example. And the bonding sigma molecular orbitals for carbon and hydrogen, they interact with pi orbitals. And therefore, this stabilizes the alkene, for example. In this particular reaction, what we get to see is we have this compound T-butyl bromide. And the carbocation is stabilized due to the sigma conjugation. Imagine if we replaced all of these CH3s with just hydrogen. There would be no sigma conjugation to speak of. And so therefore, it's going to be a lot less stable and higher in energy compared to this tertiary carbocation. Now, going on about this carbocation, if we have some sort of nucleophile just means seeking positive charge. Well, what it can do is it can either attack the carbocation, lone p orbital, or attack some sort of hydrogen. Like say, for example, in the CH3 group, it could attack a hydrogen, which creates the alkene. We're looking at the substitution SN1 mechanism for T-butyl bromide. Now, in addition to substitution reactions, I also wanted to talk about E1 and E2. So how exactly do we get said alkenes? So I already said that E1 and E2 occur when you have some sort of nucleophile that attacks the hydrogen. Say, for example, we have E2 elimination, right? This base, or the hydroxide ion, it attacks the hydrogen instead of attacking this bromine. And so what we get is we end up getting the bromine ejected, we get water, but we also get an alkene. And you can see how it compares to the SN2 reaction, where the hydroxide ion interacts with the bromine, directly leading to ejection. Now, you can draw parallels between E1, E2, and SN1 and SN2. And the reason for that is because what E1 and SN1 do is they rely on a carbocation first. As you can see in this reaction, this is going to be E1. This relies on some sort of carbocation, which is the rate determining step in both of these reactions. So, since the World Cup is currently on right now, I also wanted to give an analogy about how you can think of this. So, for SN1 and E1, say for example that you have Dembele, a French soccer player, and he tries to pass the ball to Mbappe. But if he doesn't kick the ball hard enough, it's in the middle of the field, right? And so therefore it can get easily stolen by an enemy player. However, for second order reactions, say for example that I want to hold up 1 second, I have a message here. Yeah. Anyways, for E2 and SN2, say for example, I'm a soccer player trying to tackle the ball out of an attacker's feet, right? So I can just directly tackle the player instead of having the player just leave the ball in the middle of the field. In other words, first order reactions, E1 and SN1, they rely on the carbocation being formed first, while the second order reactions do it in one go. Now, when we're talking about the exact geometries for E1 and E2, in the E1 reaction, if we want to form the carbocation, the filled carbon-hydrogen sigma bonding orbital, it has to interact with the carbon leaving group sigma anti-bonding orbital. Remember in molecular theory, if we donate electrons to an anti-bonding orbital, in a sense, that bond is pretty much broken. Now, for overlap to happen, what we need is for this carbon-hydrogen sigma bonding orbital to actually, well, overlap with the anti-bonding orbital. So both orbitals must be in the same plane, or in other words, coplanar. Now, there are two specific conformations, which are simply just variations of a molecule based on single bond rotations, that can achieve this overlap. So, specifically, the eclipse and staggered conformations can do this. And in addition, the hydrogen and leaving group must be anti to each other. We call the specific geometry as transcoplanar or antiperiplanar. We can also observe how exactly these molecular orbitals interact. Now, I also want to clarify the difference between E1 and E2. We already established that E1 simply needs a carbocation step as opposed to E2. Therefore, E1 is more favorable if we can actually form said carbocation and if no strong base is present. If there was a strong base, then E2 would have been more favorable. In addition, it's the same vice versa. E2 is more common if you cannot form that carbocation or if some sort of strong base is present. In addition, as you can see in this table, for E2, the leaving group must be anti to the hydrogen removed, showing the effects of transcoplanar geometry. So, what exactly makes elimination different from substitution? Well, say for example that you have some sort of molecule, and if you have some sort of base, it can go through either an elimination or substitution reaction. What if you want to make the elimination reaction happen more often? Well, you could just add a stronger base. The issue is, if you just have a stronger base, that'd be a stronger nucleophile, and nucleophiles substitute. So we're not even favoring the elimination reaction, right? However, if we use a really big and bulky base, say for example T-butoxide, which is found in potassium terbutyl oxide, what happens is, because it's so bulky, instead of acting like a nucleophile that can be substituted, it acts more as of a base. In addition, we instead of using potassium T-butoxide, what we can use is DBN and DBU, which are two cyclic compounds that also act as bases instead of nucleophiles. Going on about some connections to past chapters, apparently stereochemistry is important for E2. And this is because since the hydrogen and leaving group have to be transcoplanar for the E2 reaction to happen, different products can actually come from different diastereomers. As you can see, what occurs is, with this particular diastereomer, both chiral centers are in R configuration, are in R, we get a Z alkene. But if we have S and then R, we get an E alkene. I suggest reviewing the past chapter, aka chapter 14, to learn a bit more about isomerism. So I believe that's like the first 10 slides of this, so I'll give you all some time in lecture land to ask any questions. I'd be happy to answer them. Alright, it appears as if there are no questions for now, so let's get on with it. So, in addition to stereospecificity, I also wanted to talk about regioselectivity. So take a look at this image right here. We have an elimination reaction going on, but the thing is, once we have that carbocation being formed, what can occur is the base in the elimination reaction can abstract away different protons. And you can see specifically which protons the base takes away affects the product. We get alkene X and alkene Y from this. And this is directly related to regioselectivity. And this is when a reaction happens at one site compared to another. If you take a close look at this R group, based on what is actually that R group, so say for example the methyl group versus terbutyl, then that can affect the amount of alkene X that is formed and alkene Y that is formed. Next on, I also wanted to talk about the energies of some different alkenes. So just as a rule, if you have a more substituted alkene, it's going to be more stable than one that is less substituted. And that's because if you have more alkyl groups, like if you have a carbocation being formed, then due to the sigma conjugation, stabilization effects will occur. And in fact, you can see for this particular alkene, when looking at the particular molecular orbitals, sigma conjugation leads to an overall energy for the alkene being lowered, and for the HOMO to be slightly raised. Alright, so this one was particularly my favorite slide, and essentially, this touches back on sigma conjugation and how it stabilizes alkenes. So once we go back to this reaction, if we take another look at this R group, as the substituent grows larger and larger, it becomes harder to abstract, well, specifically a red proton. And therefore, if we look at the compound X, it's going to be more stable due to more sigma conjugation. However, compound Y is just the easier one to get to. And so therefore, although compound X is more stable, which is referred to as thermodynamic product, compound Y is simply more feasible to reach, which is known as the kinetic product. So here's going to be a quick practice problem. This did come from a survey that I did post and also some of my own ideas. So I decided to include some of the practice problems from the textbook for you guys to look at. So if anybody's down to do any of these practice problems, like you could just say in chat if you want to, I'm testing this out. But if you want to do it, then by all means you can go ahead and post like a photo of your workings or how exactly you got to the solution. Alright, so these are the particular solutions for the practice problem 1. And you can actually look in the textbook, and overall it's much better if you do this on your own instead of actually looking this up on like Google, for example. So these are just solutions to the first practice problem. Anyways, back onto the content. In addition to elimination reactions, we can also have electrophilic addition to alkenes. And this is because carbon-carbon double bonds are rich in electrons. And so therefore, if you have some sort of electrophile, like a proton, they can go and perform addition reactions. In this particular image below, what we see is that the preferred product yields a carbocation that is attached to the rest that's centered on carbon 1 and is attached to carbon 2 and 2 other methyl groups. We don't want a less stable carbocation where there's only going to be one carbon that's attached to the carbocation carbon. Now, going on about addition to alkenes, bromine can actually be added to alkenes. And how exactly does this work? Well, to start, what happens is we initially have an alkene and we have bromine in its diatomic form. And by the end, we have a lone bromide ion, and we have this thing known as a bromonium ion. Now, this bromonium ion has to be opened in some way. And what happens is this bromide ion, that will attack the bromonium ion from the back and eventually yield this particular product at the bottom here. And as you can see in this particular slide, there are two different ways for the bromide ion to go and attack this bromonium ion from the backside. Now, because it does do a backside attack, what we're going to have is the bromine atoms are going to be anti to each other. Or in other words, they have a dihedral angle of 180 degrees to each other. Now, when opening the bromonium ion, we see that we have the negative bromide ion, which is a nucleophile. However, do we always have to use bromide to open this ion? No. In fact, water, due to its polarity, can perform the same backside attack. And as you can see in this reaction, what occurs is we have this bromonium ion being formed, and then water attacking it, leading to a racemic mixture of basically substituted cyclohexane. Now, in these reactions that I previously showed you, we use diatomic bromine. Now, if diatomic bromine wasn't very lethal, I think we would be fine. However, it is pretty lethal. It has very toxic fumes and is highly corrosive. So, instead of using bromine in its pure diatomic form, or bromine water, what we can have instead is we can use a molecule known as N-bromosuccinimide, which provides bromine without being so toxic. Now, going on about rings, you can see this bromonium ion right here. That's pretty much a three-membered ring. You have a carbon here, and a bromine here. However, epoxides are also rings, as they are essentially just like bromonium ions, except, well, they're not really ions, and they have an oxygen here instead of a bromine. And as you can see, with this alcohol, this attacks the alkene, yielding an epoxide product. Also, a short fun fact, epoxides are highly strained due to their geometry. And because of this, they can also be opened up in a similar fashion to what we did with the bromonium ions. So if we have the basic conditions, we can send a nucleophile, and that will end up opening the epoxide, and in addition, the oxygen nucleophile will end up being anti to each other. Now, no kidding, this is because we're doing a backside attack on the epoxide. Another reaction concerning alkenes is hydroboration, where if we have an alkene, this one's supposed to be hydrated alkene in aqueous acid, what we're going to have is we're going to end up yielding an alcohol. And in addition, if we hydrate an unsymmetrical alkene in aqueous acid, what we're going to end up is we are going to get one sort of alcohol over another. You can see in this particular image that these alcohols are different from each other. And generally, by having this alkene in aqueous acid, what we end up having is something known as the Markovnikov product. Now, for those who don't know, Markovnikov's rule can be summarized by this one saying: the rich get richer. And that's because donation of a group happens to the carbon that has the least hydrogens on it. Now, what if we want the anti-Markovnikov product, where we have this completely reversed? Well, we can use a wide class of compounds known as borane. And borane simply refers to a broad class of compounds that just have boron and hydrogen. The simplest one will be BH3, which is actually electrophilic. And in addition, as a side note, I will be talking about borane in the next chapter and how it exists as a dimer. But anyways, when borane approaches an alkene, the pi electrons found in the carbon-carbon double bond, those are actually donated to the empty 2p orbital of boron. And once this happens, that boron is going to gain a negative formal charge, and it's going to keep on doing this until we get a trialkyl borane. Now, we have this pretty cool product, I'd say, but we don't want boron in our final product. We want an alcohol. And we want this alcohol to be done in an anti-Markovnikov fashion. And so what we can use is a mixture of hydroxide and hydrogen peroxide, which yields the HOO minus ion. And the lone pair on that negative oxygen, it will attack the empty orbital of the trialkyl borane, which is the empty p orbital. Now, the reason why we use this as the nucleophile in this reaction is because once we have more electron density in the alkyl groups, hydroxide will easily be repelled. Now, borane was pretty basic, so instead of that, we use a compound known as 9BBN, which has greater selectivity and overall prefers the anti-Markovnikov product a lot more. Next on, I also wanted to talk about special class of compounds known as enols and enolates. So I wanted to talk more about alkenes. So these compounds show interesting properties, from sigma conjugation to electron density being skewed for unsymmetrical alkenes. Now, imagine that we have some sort of carbonyl compound. It can either be an aldehyde or a ketone. If we have carbons that are next to that carbonyl, then sigma conjugation can pull electron density away from the carbon-hydrogen bond. Now, carbons right next to the carbonyl carbon are known as alpha carbons. And because of this, hydrogens are being easier to remove. And once a strong base comes along, it removes that hydrogen, which will then form your enolate ion right here. Now, to form enolates, you can use hydroxide, but it's not always a good base. And so stronger bases, such as lithium diisopropylamine or LDA, are needed to form enolates. Now, this one is going to touch a bit back on those alkene addition reactions. So if you want to briefly do this, I'll give about a minute or so. Just predict product A for now. Now remember, if we leave an alkene in aqueous acid, what we're going to yield is going to be the Markovnikov product. We use boranes and 9BBM for anti-Markovnikov reactions. Alright, so here is the particular product for product A. So remember that Markovnikov's rule can be summed up by the rich get richer. And what we're going to have is we're going to have this alcohol functional group substituted onto this more substituted carbon instead of this carbon, which has more hydrogens on it. Anyways, going on about enols and enolates, ketones and enols exist in an equilibrium. And as you can see, we have this ketone compound, acetone, and it can actually convert into its enol compound, which can then be deprotonated to form an enolate. Now, going on about enolates, what happens is thermodynamics and kinetics can affect it. And so, for example, with this particular base and this particular ketone, we can abstract away different protons, as you can see, and we get both a thermodynamic and kinetic product. This is going to be the thermodynamic product, remember, because it is more stable. As you can see, there's going to be some more sigma conjugation here. However, for this kinetic product, it's going to be less stable, but it's going to be feasible. And that's what matters, even if the thermodynamic product is more stable. Now, looking at the molecular orbitals for enols and enolates, we're going to look at the HOMOs, or highest occupied molecular orbitals. And using these particular plots, we can observe that for enolate ions, electron density is going to be on alternate atoms in that particular pi system, or in this little double bond here. And in addition, we're going to have the greatest electron density be on the carbon. The HOMOs for enols and enemies, which are another class of compounds similar to enols, are similar, but there's going to be a bit more electron density between those two carbon atoms. Now, enolates can actually go through a particular reaction known as alkylation, where we simply just add an alkyl group. So, say for example, that we have this particular ketone. We just look at reaction A. We can use sodium amide, and from this ketone, we can get an enolate. And by reacting an alkyl bromide, what we obtain with alright yield, 62%, not bad, depending on the context, we actually get alkylation happening here. And this even happens for something such as reaction D, where we have this enamine, which is similar to an enol. We have this enamine being formed and alkylation happening after that. In addition to enolates being alkylated, they can also be brominated. So we did see that previously alkenes can react with bromine, which, well, that was pretty cool, but enols and enolates, they can also react with bromine. However, they're incapable of forming 1,2-dibromo products. Now, this is particularly because when you look at the carbon-carbon double bond, electron density will be skewed, thus preventing the formation of these products. Alright, so this is going to be pretty much practice problem number 3. I'm going to personally look at it to solve problem A myself, but I will give you all a bit of time if you guys want to do it. Alright, going on, I forgot to put the solution there, but going on, aromatic, we're going to talk about aromatic molecules. In this particular section is going to be specifically devoted to reactions where we have some sort of hydrogen on a benzene ring that's substituted for another group. So benzene is pretty much a hexagonal compound that has a delocalized pi electron system. And although it appears as if it has these isolated double bonds, so like for example these other cyclic compounds, its reactivity is different due to pi conjugation. And in fact, even when alkenes react quickly with bromine, benzene doesn't even react that quickly with bromine, even with a catalyst present. And in addition, that pi system, that delocalized pi system, is going to add some extra stability. And in addition, when it comes to alkene addition reactions, for example, that pi system is often going to be lost. But for something like aromatic addition reactions, that pi system is usually going to stay as compared to alkenes. Now, I also want to talk about what aromatic compounds are. And these are just compounds that contain pi conjugated rings and follow a particular rule known as Huckel's rule. And even if there are conjugated rings, so say for example cyclobutadiene or cyclooctatriene, what's going to happen is, although they are conjugated, they're unstable and they're not going to be aromatic. And that's because they don't follow Huckel's rule. So looking at the pi molecular orbitals of benzene, we can see that if you analyze this using something like Huckel molecular orbital theory, when I studied it, it was pretty cool to look at. There's also that one circle. I did forget the name of that circle, but it is pretty neat. And essentially, we can see that based on the combination of these p orbitals, we get different molecular orbitals. So the lowest energy molecular orbital has all of the p orbitals in phase, while the highest energy one has them all out of phase. And in addition, we have two pairs of degenerate orbitals. Now, these bonding molecular orbitals, all the electrons are going to nicely fit in pairs here, you know? There's going to be spin up electron here, spin down electron here, spin up electron here, spin down electron here. Everything's fine. Unfortunately, it's not going to look good for this other compound known as cyclobutadiene. And that's because if you look at its square geometry, that one pair of degenerate molecular orbitals, they're going to be non-bonding, and well, according to Hund's rule, you have to line these electrons up, spin up. And so what we're going to have is we're going to have these electrons spinning, these electrons not in a pair, right? And so if you distort that, a cyclobutadiene into a rectangle, that energy is going to be lowered and we get these electrons in pairs, meaning that we get extra stability. Oh yeah, thank you. Yeah, those are called Frost diagrams. I did forget the name. But yeah, if you guys have any questions that I put them in lecture land, I'd be happy to answer them. I'm gonna stop right here briefly. Alright, there appear to be no questions, so we'll go on to the next final parts of this lecture. So going on about Huckel's rule, say for example, if we have n2p orbitals, n just means number. If you have some number of 2p orbitals in a cyclic pattern, then the lowest energy molecular orbital will be non-degenerate. However, the rest of the molecular orbitals will be degenerate, meaning that we're going to have pair orbitals that have the exact same energy. Now, the only exception to this is if we have an even number of orbitals. In that case, the highest energy orbital is going to be non-degenerate. Now, since it takes 2 electrons to fill the lowest energy molecular orbital, and 4 for every degenerate pair, then the amount of pi electrons needed for aromaticity gonna follow this pattern: 2, 6, 10, 14, and so on. And this is formalized in Huckel's rule, where for aromaticity to be valid, you need a conjugated cyclic ring, but you also need, in that ring, 4n plus 2 pi electrons. And n is going to be a whole integer. So n can't be something like 1.5 or 1.75. It has to be an integer. Alright, so what about the reactions for these aromatic systems? Well, I already said that compared to alkenes, benzene and other aromatic compounds retain their pi system. Now, I want you to look at this reaction. If you mix phenol, which is essentially just an alcohol group slapped onto a benzene ring, then if you mix that with deuterated acid and water, then some of those hydrogens on the benzene ring will be exchanged for deuterium. And what basic conditions do is where the alcohol group is going to be deprotonated and we're just going to have a negative oxygen. Keep in mind that these particular areas are going to be of interest once we get into substitution. And that's because these particular areas are known as ortho or para positions. And because they have greater electron density, it's much easier for deuterium to be substituted into these positions, which is here, here, and here relative to this. However, if you attack via this meta position, which is here and here, this is going to be harder, and you're going to have to overcome a greater energy barrier. So we do know that electron density affects whether will there be recording for this lecture? Yeah, there will be a recording, absolutely. You will see it on YouTube. Expect it, I'd say pretty soon. I usually post my stuff like right after I give the lecture. Alright, but anyways, did you also know that the size of substituent can affect whether a compound is substituted at either the meta, ortho, or para positions? And you can see different substituents on these benzene rings can affect reaction rates at ortho or para positions. I also wanted to talk about the effects of electron withdrawing groups. And so, if there are groups that withdraw electron density from the pi system, instead of addition happening at either the ortho or para position, what we're going to have is addition at the meta position. Going on, I want to talk about bromination. And so, if you just have benzene, like just plain benzene, and you reacted with diatomic bromine, not much is going to happen. But if you have some sort of activating group on a benzene ring, so say for example an alcohol, then bromination can be a lot more rapid. Now, I also wanted to talk about alkylation. And this particular reaction is going to be called Friedel-Crafts alkylation. So, compared to something like alkenes, right? Aromatic systems will either need a more reactive electrophile or some sort of Lewis acid catalyst. Lewis acid are simply electron acceptors. And so in Friedel-Crafts alkylation, we take some sort of alkyl halide and we react it with aluminium chloride to form some sort of carbocation. And because this carbocation is, well, a Lewis acid pretty much, it's going to form a complex with this benzene ring, which is then deprotonated, which will then restore aromaticity, and boom, now you have an alkyl group substituted onto your benzene ring. However, there are issues with this reaction, and that's because, say for example, alkylation occurs. If you have an aromatic system and it's alkylated, what's going to happen is the product is going to be a lot more reactive, meaning that substitution will occur many times over. And in addition, the carbocation created from aluminium chloride and the alkyl halide can change due to preferences in lowering energy. Remember that the greater the degree of a carbocation, the more stable it is. And therefore, in some sort of hydride shift, what happens is that carbocation is going to shift even before it reacts with the aromatic system, which messes things up. So what about acylation? Not alkylation, but acylation. So compared to alkylation, acylation is a lot less problem riddled. And so what we're going to have is we're initially going to have aluminium chloride and acyl chloride, which is a class of compounds that I discussed back in chapter 11. And so the HOMO of the acyl chloride will react with the lone p orbital of AlCl3, which sort of is covalent. And this will create something known as an acylium ion, which will create a much more controlled mechanism. And finally, using a mixture of nitric and sulfuric acids, as you can see in this particular image, you can nitrate benzene rings. Now, for this particular reaction, the ortho and pair positions are preferred to meta when it comes to nitration. So, to sum this crazy chapter up, elimination reactions can form alkenes. You can draw parallels with E1 and E2 and SN1 and SN2. And in addition, we have special reactants such as potassium tert-butoxide that will prefer elimination instead of substitution. Our second point is that enols and enolates are related to carbonyl compounds and therefore can be alkylated. Finally, aromatic molecules can have great stability compared to alkenes and are involved in several different reactions, as in Friedel-Crafts alkylation or Friedel-Crafts acylation. So here's going to be the fourth practice problem. We're honestly pretty much done with the chapter, so if you want, I can give you a quick opportunity to screenshot it, or if you want to solve that on your own. Alright, here's also the solution if you want to screenshot that. Alright. And yeah, that's going to pretty much end the lecture. So we're going to finally get out of organic chemistry, and we're going to talk about an even better subject next chapter, which will be inorganic chemistry, specifically main group reactions. And I did take a quick look at it, and this does involve a bit more ML theory and equilibrium to be involved, and not so much memorization. And so that pretty much is going to sum up everything for chapter 15.